Next, we're going to look at a general procedure for deriving the power series for a function that has derivatives of all orders, and specifically we're going to be looking at two types of series, power series, Taylor series and Maclaurin series. This theorem is going to describe the form that every convergent power series must take. So it's as if f is represented by a power series f of x equals the sum of a sub n times x minus c to the nth power for all x in an open interval I containing c, then a sub n can be written as the nth derivative of f at c divided by n factorial. And f of x could be written as f of c plus f prime of c times x minus c to the first power plus f double prime of c divided by 2 factorial times x minus c squared, all the way down to the nth derivative and the nth power, all the way down to infinity. And of course the implication here is that this is divided by 1 factorial and this one is divided by 0 factorial, and you have x minus c to the 0 power. So it's taking that form all the way across, you just don't really see it in the first two terms. And this is actually the definition of the Taylor series for f of x at c. So if a function f has derivatives of all orders at x equals c, then the series given by that form that we just talked about is called the Taylor series for f of x at c. And if c equals 0, then this series is called the Maclaurin series for f. So a Maclaurin series is just a very particular Taylor series where c is equal to 0. So this example says use the function f of x equals cosine of x to form the Maclaurin series, the sum from 0 to infinity, blah, 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 which is where we're plugging in a 0 here for c, and determine its interval of convergence. So I'm going to get a couple of derivatives, so I just kind of know what's going on with our f of x. So if f of x equals cosine of x, f prime of x would be negative sine of x, f double prime of x would be negative cosine of x, the third derivative would be positive sine of x, because you cancel the negatives out. The fourth derivative would be cosine of x. And then you'll notice what happens here is we just kind of keep cycling back through. So just getting down to like maybe the sixth derivative, you can see the cycle that's starting to happen. And that can be done infinitely many times. You'll just follow this same basic cycle over and over and over again. Okay, so according to how this works, f of x, which is the sum from 0 to infinity of the nth derivative at 0 divided by n factorial x to the n, okay, is actually, for n equals 0, we'll have cosine of 0. For n equals 1, we'll have the derivative of that, so that'll be negative sine of 0 x. And then for the third derivative, we would have, for the second derivative, we would have negative cosine of 0 x squared over 2 factorial. And then we would have sine of 0 x cubed over 3 factorial, and so on and so forth, as many terms as you need to see the pattern. Let's do one more. Let's go at least out to, for n equals 4, we would have the cosine of 0 x to the 4th over 4 factorial. Okay, just looking at those derivatives. So however you need to determine the sine and the cosine of 0, I like to look at a unit circle. So this is 0, 1. So we'll have 1, that is 1, 0. Hopefully you caught that. We'll have 1 plus negative 0x plus negative 1 over 2 x squared plus 0x cubed over 6 plus 1 x to the 4th over 24, and so on and so forth, or 1, and let's just go ahead and write that as factorials here. I've got minus 1 over 2 factorial x squared, and then this one goes away, and I've got plus 1 over 4 factorial x to the 4th, we would skip the fifth term again. We'd have minus 1 over 6 factorial x to the 6 if you wrote the next terms out. I hope you can kind of see what's happening here. So this was what happened when I had my original n equals 0, n equals 1, n equals 2, but let's rewrite it where this is n equals 0, this is n equals 1, this is n equals 2, and this is n equals 3. So if I do that, my pattern now becomes the sum from 0 to infinity of an alternating negative 1 to the nth power, because this would be 1, negative 1, 1, negative 1, okay, divided by 2n factorial. This would be 0 factorial, 2 factorial, 4 factorial, 6 factorial. And then we'll do x to the 2n power. So if n equals 1, we'd have x squared. If n equals 2, we'd have x to the 4th. If n equals 3, we'd have x to the 6th. So this is going to be my power series. Now the only thing that's left is to determine the interval of convergence. And so this one is not a geometric series. I'm going to use the ratio test. And I know that I'm going to have the limit as n approaches infinity of u sub n plus 1 over u sub n in absolute value bars. So u sub n plus 1 here, we're not going to need the negative 1s, so we'll have, we'll have x to the 2n plus 2 divided by 2n plus 2 factorial, that's my u sub n plus 1, times 2n factorial over x to the 2n power. So I'll have x to the 2n times x squared. Breaking this down, I'll have 2n plus 2 times 2n plus 1 times 2n factorial times 2n factorial over x to the 2n. Cancel what cancels. And I get the limit as n approaches infinity of the absolute value of x squared over 4n squared plus, let's see, that'll be 6n plus 2. And since we're taking the limit as n approaches infinity and there's no n in the top but there's an n squared in the bottom, that is 0, which is less than 1 for all x. So our interval of convergence is negative infinity to infinity. All real numbers here. So that would be our power series. Now this is important. We did find that this power series converges for all real values of x, but we cannot conclude that the power series converges specifically to cosine of x for all x. We just know that it converges to some function. So just kind of keep that in mind. You can't necessarily say that this is equal to cosine of x for all values of x, just that it does converge. And from our discussion of remainders, we know that for each n, you end up with that r sub n of x at the end, which is the nth term, and or which is the remainder after the nth term. And we know that that gives you kind of an approximation of what you could find there, and that would be the n plus first derivative at some z over n plus 1 factorial, where x minus c is to the n plus first power. So you have that portion of it as well. So if you figure this out, and this r sub n term here, if the limit as n approaches infinity of this is equal to 0 for all x in the interval I, then the Taylor series for f converges and equals f of x. So another way to state this theorem is to say that a power series formed with Taylor coefficients, a sub n equals the nth derivative of f at c divided by n factorial, converges to the function from which it was derived precisely at those values for which the remainder approaches 0 as n approaches infinity. So there is a way to determine which values, or for which values this thing converges to what you expect it to. So we'll show an example where we demonstrate that it does converge to what we expect it to in a little bit. So these are some guidelines for finding a Taylor series. It's basically just the process that we went through. We find the derivatives and we try to recognize a pattern. We build those coefficients with the n factorial and so on and so forth. And then we determine the interval of convergence and determine whether the series converges to f of x within that interval of convergence. So let's do an example. It says use the definition to find the Taylor series centered at c equals 0 of f of x equals e to the 2x. So I'm just going to find a couple of derivatives so we can kind of start to see a pattern. I know that f prime of x here would be 2 e to the 2x. I know that the second derivative would then be 4 e to the 2x. The third derivative would then be 8 e to the 2x. And the fourth derivative would then be 16 e to the 2x. If you don't see the pattern yet, you can keep going, but I see it here. I see that we're saying 2 to the first power e to the 2x. We're saying 2 squared e to the 2x, 2 cubed e to the 2x, and 2 to the fourth e to the 2x. So my f's of 0 would be just the 1, because I'd plug in f of 0 equals e to the 0 power. F prime of 0 times x minus 0 divided by 1 factorial would be 2 e to the 2, or 2 e to the 0 times x. The second derivative at 0 times x minus 0 squared over 2 factorial is going to give me the 4 e to the 0 x squared over 2 factorial. The next one would give me the 2 to the, so this one was 2 squared, so this will be 2 cubed e to the 0 x cubed over 3 factorial. And I see the pattern. This is going to be the sum from 0 to infinity of, these are all 1 here. So we'll have 2 to the nth power, x to the nth power, over n factorial. So then the question is, does this series converge to f of x? So over here you can see I've used the ratio test and just quickly determined the interval of convergence. We've done these enough times, but if you need to pause the video and convince yourself that you do get an interval of convergence from negative infinity to infinity, and you can see how I've worked that out there. So the thing that we're going to find next then to answer this question, does the series that we found converge to f of x, we're going to take the limit as n approaches infinity of r sub n of x, which is going to be the limit as n approaches infinity of f to the n plus first derivative of that at 0, divided by n plus 1 factorial and x to the n plus 1 power. And we know that the n plus first derivative is going to be 2 to the n plus first power, so we'll have the limit as n approaches infinity of 2 to the n plus first power times e to the 0 power, so we'll just leave that out, x to the n plus 1, all over n plus 1 factorial. And you can plug numbers into this and test. You can observe that factorials grow faster than these exponentials do, but this, or you could use something like L'Hopital's rule would be kind of complicated with a factorial, but factorials grow faster than 2 to a power or x to a power. So this is equal to 0, and since that is what the theorem wanted, then we can say that yes, this converges to f of x equals e to the 2x for all real x in the interval from negative infinity to infinity. So this is our Taylor series, and it does converge as we expect.